Have you ever wondered how scientists manage to measure the vast distances to the stars? It's a question that has intrigued humanity for centuries, and the answer lies in something you experience every day. Imagine you're sitting on a moving train, gazing out the window at the passing landscape. You'll notice something fascinating. The nearby trees and buildings seem to zip past quickly, while distant mountains barely appear to move at all. This simple observation, known as parallax, holds the key to unlocking the mysteries of cosmic distances. This same principle that makes nearby objects appear to move faster than distant ones has become one of astronomy's most powerful tools. When you're on that train, you're witnessing the same phenomenon that astronomers use to measure the unfathomable distances to the stars. Just as the trees and mountains shift positions relative to each other as you move, stars shift their apparent positions as Earth orbits the Sun. In 1838, a groundbreaking moment in astronomical history occurred when Friedrich Bessel achieved something remarkable. Using this principle of parallax, he successfully measured the distance to 61 Cygni, the first star ever measured beyond our solar system. This wasn't just another scientific measurement, it was a revolutionary discovery that transformed our understanding of the cosmos. Before Bessel's work, stars were mysterious points of light that many believed were attached to a celestial sphere surrounding Earth. His measurement proved definitively that stars are distant suns, scattered through the vast depths of space at almost unimaginable distances. Today, we're going to unravel the genius behind stellar parallax, a method that has become fundamental to modern astronomy. What makes this technique particularly elegant is that it relies on nothing more complex than basic geometry, the same principles you might have learned in high school. Combined with careful observation and plenty of patience, this method has allowed us to create a three-dimensional map of our cosmic neighborhood. The beauty of stellar parallax lies in its simplicity. We don't need elaborate equipment to understand its basic principle, though measuring stellar distances does require precise instruments. This method has become our cosmic yardstick, our first step in understanding just how vast our universe truly is. If you're fascinated by how we've managed to unlock these cosmic secrets, if you're curious about how we've learned to measure the seemingly immeasurable, then you're in for a treat. Join us on the Exploring the Universe channel, where we continue to uncover the wonders of the cosmos, one discovery at a time. This is just the beginning of our journey through space and time. Let's start with a simple experiment you can do right now, wherever you are. Hold your thumb up at arm's length and look at it with your right eye while keeping your left eye closed. Now, without moving your thumb, switch eyes. Close your right eye and open your left. Notice how your thumb appears to jump against the background. This simple trick demonstrates the fundamental principle of parallax, the same method astronomers use to measure distances to stars. What's happening here is fascinating. Your thumb didn't actually move. Instead, by switching between eyes, you changed your observing position by about 2.5 inches, the average distance between human eyes. This change in perspective makes your thumb appear to shift position relative to objects in the background. The closer your thumb is to your face, the larger this apparent shift becomes. Try it again, but this time hold your thumb closer to your face. Notice how the apparent jump is much larger? This is a key principle in parallax measurements. The closer an object is, the larger its apparent shift when viewed from different positions. Now let's scale this up to astronomical proportions. Instead of using the distance between our eyes as a baseline, astronomers use Earth's orbit around the Sun. As our planet travels through space, it creates a massive baseline of approximately 186 million miles in diameter. By observing a nearby star at 6-month intervals, when Earth is on opposite sides of its orbit, astronomers can measure the tiny shift in the star's apparent position against the background of more distant stars. This apparent shift creates what we call the parallax angle. Imagine drawing two lines from Earth's positions on opposite sides of its orbit to a nearby star. These lines form a triangle, with the star at the apex. The angle at this apex is the parallax angle, and it's incredibly small. Even for the closest stars, it's less than 1 arcsecond, or 1/3600th of a degree. To put this in perspective, it's like measuring the width of a quarter from about 3 miles away. The smaller this angle becomes, the more distant the star is. In fact, the relationship between parallax angle and distance is beautifully simple. The distance to a star in parsecs is just 1 divided by the parallax angle in arcseconds. This is why astronomers created the parsec unit. It elegantly connects these geometric measurements to actual distances in space. For an even more tangible demonstration, try this at home. Place a small object like a pencil on a table about arm's length away. Now, keeping your head still, look at the pencil with just your left eye, then just your right eye. The pencil appears to shift position relative to objects further away on the table. This is exactly what astronomers do, but instead of using their eyes, they use Earth's position in January and then again in July to create their baseline. Understanding this basic concept of parallax opened the door to measuring our cosmic neighborhood. It was our first reliable method for determining stellar distances, and it remains one of the most fundamental and accurate techniques in modern astronomy. While today we have sophisticated satellites like Gaia that can measure parallax with incredible precision, the basic principle remains exactly the same as the thumb experiment you just performed. When we scale up our understanding of parallax to cosmic distances, the fundamental principle remains the same, but the numbers become truly astronomical. Instead of using the distance between our eyes as a baseline, astronomers harness something far more powerful: Earth's entire orbit around the Sun. This gives us a phenomenal baseline of approximately 186 million miles, the diameter of Earth's orbit. Think about that for a moment. We're using our planet's cosmic dance around the Sun as a cosmic measuring tape. But why do we wait exactly 6 months between measurements? The answer lies in simple geometry. After 6 months, Earth has traveled to the exact opposite side of its orbit around the Sun, giving us the maximum possible baseline for our measurements. Imagine drawing a straight line through space. When Earth is at one end of this line in January, we take our first measurement. Then we wait patiently until July, when Earth reaches the opposite end of this line, to take our second measurement. This gives us the widest possible viewing angle, making our measurements as accurate as possible. During these 6 months, nearby stars appear to shift their position ever so slightly against the background of more distant stars. This shift is incredibly small, so small that it went undetected for centuries. Even for the closest stars, we're talking about angles smaller than 1 arcsecond. To put this in perspective, 1 arcsecond is equivalent to the width of a human hair viewed from about 65 feet away. The fact that we can measure such minute angles is a testament to the incredible precision of modern astronomical instruments. This brings us to one of astronomy's most elegant units of measurement, the parsec. The term parsec is a combination of parallax and arcsecond, and it's defined as the distance at which an object would have a parallax angle of 1 arcsecond. 1 parsec equals approximately 3.26 light-years, or about 19 trillion miles. The beauty of the parsec is its direct relationship to parallax measurement. If a star has a parallax angle of half an arcsecond, it's 2 parsecs away. A parallax of 1/4 arcsecond, that's 4 parsecs. The relationship is beautifully inverse and straightforward. Let's put this into perspective with some real numbers. Proxima Centauri, our nearest stellar neighbor beyond the Sun, has a parallax angle of 0.7687 arcseconds, placing it at a distance of about 1.3 parsecs or 4.2 light-years. That's over 25 trillion miles, and this is just our closest neighbor. Most stars we can see with the naked eye are hundreds or even thousands of parsecs away, with correspondingly tiny parallax angles. Speaking of nearby stars, this brings us to an interesting question. What's the closest star you know about? While many might immediately think of the North Star or Sirius, the brightest star in our night sky, our actual closest stellar neighbor is Proxima Centauri, a tiny red dwarf star too faint to see without a telescope. Sirius, despite being the brightest star in our night sky, is actually much further away at 8.6 light-years. The parallax method has its limitations. It becomes less accurate for very distant stars because their parallax angles become too small to measure reliably. However, for stars within about 1,600 light-years, it remains one of our most reliable distance measuring tools. Modern space-based observatories like Gaia have revolutionized parallax measurements, allowing us to measure distances to millions of stars with unprecedented precision. This is where you come in. We'd love to hear from you. What's the closest star you know about? Have you ever seen Sirius blazing in the night sky? Share your astronomical knowledge and observations in the comments below. Let's create a conversation about our stellar neighbors and continue exploring the wonders of our cosmic backyard together. The story of stellar parallax is a testament to human perseverance in the face of seemingly impossible challenges. For centuries, astronomers struggled to detect any measurable parallax in stars, leading some to question whether Earth truly orbited the Sun. The challenge was immense. They were trying to measure angles so small that no instruments of the time could detect them. Enter Friedrich Wilhelm Bessel, a German astronomer who would change our understanding of the cosmos forever. In 1838, after years of meticulous observations, Bessel successfully measured the first stellar parallax for 61 Cygni, a relatively unremarkable double-star system. You might wonder why he chose this particular star. While not the brightest or most prominent, 61 Cygni had caught astronomers' attention due to its relatively rapid motion across the sky, suggesting it might be nearby. Bessel's measurement revealed the star to be about 4 light-years away, remarkably close to the modern value of 11.4 light-years. The instruments Bessel used would seem primitive by today's standards. His primary tool was a heliometer, essentially a telescope with a split lens that could measure tiny angles by comparing the positions of different stars. Each measurement had to be made manually, requiring incredible patience and precision. The margin of error was significant, but Bessel's careful methodology and statistical analysis allowed him to achieve a reliable result. Early parallax measurements faced numerous challenges. Earth's atmosphere distorted observations, making precise measurements difficult. Temperature changes could affect instrument calibration, and mechanical limitations meant that only the nearest stars could be measured with any accuracy. Despite these obstacles, pioneering astronomers like Thomas Henderson and Friedrich Georg Wilhelm von Struve joined Bessel in successfully measuring parallaxes to other nearby stars, gradually building our first three-dimensional map of the local stellar neighborhood. The field of parallax measurement remained relatively unchanged until the late 20th century, when space-based astronomy revolutionized our capabilities. The launch of the European Space Agency's Hipparcos satellite in 1989 marked a quantum leap forward. Operating above Earth's atmosphere, Hipparcos measured parallaxes for more than 100,000 stars with unprecedented precision. What had taken centuries of ground-based observations could now be accomplished in a matter of years, with accuracy hundreds of times better than what Bessel could achieve. But Hipparcos was just the beginning. In 2013, the ESA launched Gaia, a space observatory that has transformed our understanding of the Milky Way. Gaia is nothing short of revolutionary. It's measuring the positions, distances and motions of over 1 billion stars with precision that would have seemed impossible just decades ago. To put this in perspective, Gaia can measure angles as small as 20 micro-arcseconds, equivalent to seeing a human hair from 1,000 kilometers away. The impact of Gaia's observations has been profound. We're not just measuring distances anymore. We're creating the most detailed three-dimensional map of our galaxy ever attempted. Gaia has revealed previously unknown stellar streams, mapped the spiral arms of our galaxy, and even helped us understand the Milky Way's collision history with other galaxies. This evolution from Bessel's heliometer to Gaia represents more than just technological progress. It's a story of human ingenuity and determination. What began as a quest to measure the distance to a single star has become a comprehensive survey of our galactic neighborhood. Each advancement in our measurement capabilities has revealed new mysteries and sparked fresh questions about our place in the cosmos. The same basic principle that Bessel used, parallax, remains at the heart of these measurements, but our ability to apply it has expanded beyond anything the pioneers of astronomy could have imagined. Looking back at this journey, from manual observations through telescopes to automated space-based measurements of billions of stars, we can appreciate both how far we've come and how much remains to be discovered. Each generation of astronomers has built upon the work of their predecessors, gradually pushing the boundaries of what's possible in our quest to understand the vast cosmic ocean we call home. The parallax method has revolutionized our understanding of the Milky Way in ways that would have astonished early astronomers. Thanks to modern parallax measurements, particularly from the Gaia mission, we've transformed our view of the galaxy from a flat, artistic impression into a dynamic, three-dimensional reality that we can explore with unprecedented precision. Creating a 3D map of the Milky Way is akin to mapping a vast city while being inside it. Parallax measurements serve as our cosmic GPS, pinpointing the exact locations of stars in three-dimensional space. By combining millions of these stellar positions, we've discovered that our galaxy is far more complex and dynamic than previously thought. The Milky Way isn't just a simple spiral, it's a dynamic structure with multiple arms, mysterious ripples, and unexpected warps in its disk. One of the most surprising discoveries came when astronomers found that our galaxy's disk isn't flat at all. It's warped and twisted, particularly at its edges, like a vinyl record left out in the sun. This revelation was only possible because parallax measurements allowed us to precisely locate stars above and below the galactic plane. We've also discovered that the Milky Way's spiral arms aren't evenly distributed or uniformly shaped. Instead, they show asymmetries and features that suggest a violent history of galactic collisions and interactions. The precision of modern parallax measurements has revealed something even more fascinating: stellar streams. These are ribbons of stars that wind through our galaxy like cosmic rivers, remnants of smaller galaxies and star clusters torn apart by the Milky Way's gravitational forces. These streams tell the story of our galaxy's formation and evolution, showing how it has grown by consuming smaller galaxies throughout its history. But parallax is just the beginning of our cosmic measuring toolkit. Modern astronomers combine parallax data with other sophisticated techniques to build an even more complete picture. Spectroscopy, for instance, allows us to determine a star's chemical composition and radial velocity, its motion toward or away from us. When combined with parallax measurements, this gives us a complete picture of stellar motion in 3 dimensions. Another crucial technique is photometry, which measures a star's brightness and color. When combined with precise parallax distances, these measurements allow astronomers to create what we call the Hertzsprung-Russell diagram, a fundamental tool for understanding stellar evolution. This diagram has revealed distinct populations of stars within our galaxy, each telling its own story about the Milky Way's history. The impact of these combined measurements extends far beyond just mapping stars. They've helped us understand the distribution of dark matter in our galaxy by revealing how stars move under its invisible influence. We've discovered that the Milky Way's dark matter halo is slightly lopsided, possibly due to ancient galactic collisions. These findings have profound implications for our understanding of galaxy formation and evolution. Perhaps most excitingly, precise parallax measurements have revealed the presence of previously unknown stellar nurseries, regions where new stars are being born. We've found that star formation isn't uniformly distributed throughout the galaxy, but occurs in specific regions, often along spiral arms or at the interfaces of colliding gas clouds. This has given us new insights into how stars form and how our galaxy continues to evolve. The combination of parallax with other measurement techniques has also revolutionized our understanding of exoplanets. By precisely measuring a star's distance and apparent motion, we can better detect the subtle wobbles caused by orbiting planets. This has helped confirm numerous exoplanet discoveries and provided more accurate measurements of their properties. Looking toward the future, the impact of parallax measurements continues to grow. As we process more data from Gaia and combine it with observations from other telescopes and instruments, new patterns and structures emerge. We're discovering that the Milky Way is part of a complex cosmic web of galaxies, all interacting and influencing each other's evolution. One particularly fascinating application is in the field of galactic archaeology. By combining precise stellar positions with chemical composition data, astronomers can identify groups of stars that were born from the same giant molecular clouds billions of years ago. These stellar siblings, now scattered across the galaxy, help us reconstruct the Milky Way's formation history, much like archaeological artifacts help us understand human history. The story of modern parallax measurements is far from over. Each new dataset reveals unexpected features and poses new questions. Are the ripples we see in the galactic disk the result of a past collision with a dwarf galaxy? How do the newly discovered stellar streams affect our understanding of galaxy formation? These questions drive further research and technological development, promising even more discoveries in the years to come. Through these modern applications of parallax, combined with other astronomical techniques, we're not just measuring distances anymore. We're uncovering the dynamic history and ongoing evolution of our cosmic home. It's a testament to how far we've come from simply gazing at the stars to truly understanding our place among them. Perhaps the most mind-bending revelation that parallax measurements have given us is the profound understanding of time and space in our night sky. When you gaze up at the stars tonight, you're not seeing them as they are now, but as they were when their light began its incredible journey to Earth. Thanks to parallax measurements, we know with remarkable precision just how long ago that light began its voyage through space. Consider this astonishing fact. Some of the stars you see twinkling in the night sky may have already died in spectacular supernovae, yet their light continues to reach us, like cosmic ghosts haunting our view of the universe. The star Eta Carinae, for instance, located about 7,500 light-years away, a distance we know thanks to parallax, could have already exploded. The light we're seeing from it tonight began its journey when human civilization was just beginning to develop complex societies. The implications are even more profound when we consider the stars visible to the naked eye. Take Deneb, one of the brightest stars we can see, shining brilliantly in the constellation Cygnus. Parallax measurements reveal it's about 2,600 light-years away. This means we're seeing Deneb as it appeared when the Roman Empire was still centuries in the future. The light currently reaching your eyes began its journey during the Iron Age, while humans were just learning to work with metal tools. But here's where it gets truly fascinating. Parallax measurements have shown us that some stars are so massive and burning their fuel so rapidly that they simply cannot exist for more than a few million years. When we identify such stars at distances of thousands of light years, we're faced with an incredible realization. We might be witnessing their final moments, even though those moments actually occurred when our ancestors were still developing agriculture. The great eruption of Eta Carinae in the 1840s serves as a perfect example of this time delay. When astronomers observed that massive outburst, they were actually watching an event that had occurred in the early Middle Ages. The light from that eruption had traveled through space for about 7,500 years before reaching Earth. Even more intriguing, we don't know what Eta Carinae looks like right now. We'll have to wait another 7,500 years to see its current state. This realization fundamentally changes how we think about the night sky. Every star we see represents a different moment in history, creating a kind of temporal mosaic above our heads. The closest stars we can see with the naked eye, like Alpha Centauri, show us their state from just a few years ago. Meanwhile, the more distant stars visible in our sky are showing us light from decades, centuries, or even millennia in the past. Through parallax measurements, we've essentially created a time machine that allows us to peer into different moments of cosmic history simultaneously. When you look at the constellation Orion, you're not seeing a group of stars as they exist together in space and time. Instead, you're seeing a collection of stellar images from different periods in history, all arriving at your eyes at the same moment. This understanding has profound implications for our study of stellar evolution and cosmic events. When astronomers observe a supernova in a distant galaxy, they're not just seeing an explosion, they're witnessing an echo from the distant past, an event that might have occurred before humans even existed. The precise distances provided by parallax measurements help us place these cosmic events in their proper temporal context. Perhaps most humbling is the realization that our view of the universe is always historical. We can never see the cosmos as it is now. We can only see it as it was. The farther we look, the deeper into the past we see. This cosmic time delay, confirmed and quantified by parallax measurements, reminds us that we're not just observers in space, but also travelers in time, witnessing the epic story of our universe as it unfolds across the ages. This revelation transforms our relationship with the night sky. Each star becomes not just a point of light, but a window into a specific moment in cosmic history. The next time you look up at the stars, remember, you're not just looking out into space, you're looking back in time, witnessing light that has traversed unimaginable distances to reach your eyes, carrying with it ancient messages from the cosmos. When we gaze up at the night sky, we're participating in a ritual as old as humanity itself. But unlike our ancestors, who could only wonder about the distant points of light above, we now possess something remarkable, the ability to measure and understand these cosmic distances. The parallax method isn't just a scientific technique, it's humanity's first successful attempt to reach out and touch the stars with our minds. Think about what happens during a typical evening stargazing session. That faint starlight falling on your retina has traversed unimaginable distances through the void of space. The photons that allow you to see Sirius, our night sky's brightest star, have traveled 8.6 light-years to reach you. That's not just a number. It's 50 trillion miles of cosmic journey, a distance so vast that our minds struggle to comprehend it. Yet through parallax, we can measure this distance with remarkable precision. The human element of this achievement cannot be overstated. When Friedrich Bessel first measured the parallax of 61 Cygni, he wasn't just solving a mathematical puzzle, he was answering one of humanity's oldest questions: how far away are the stars? This breakthrough transformed our relationship with the cosmos. No longer were we merely observers of a mysterious celestial dance, we became cosmic cartographers, mapping our place in the universe. Consider how parallax connects to our everyday experience. When you're walking down a street, you naturally use parallax to judge distances. the way nearby buildings seem to move quickly past you while distant mountains barely shift. This same intuitive understanding that helped our ancestors hunt and navigate has now been refined into a precision tool for cosmic exploration. It's a beautiful example of how human intuition and scientific method can work together to unlock the universe's secrets. The personal impact of understanding stellar distances through parallax can be profound. When you realize that the light from Proxima Centauri, our nearest stellar neighbor, takes 4.2 years to reach Earth, you're experiencing a perspective shift that changes how you view your place in the cosmos. The stars are no longer just points on a celestial sphere. They become real places, scattered through the vast three-dimensional space of our galaxy. This understanding creates a unique form of cosmic humility. Each time we use parallax to measure a star's distance, we're reminded of the immense scales of space and time that surround us. The method reveals not just distances, but the fundamentally three-dimensional nature of our cosmic neighborhood. We're not looking up at a celestial ceiling. We're looking out into a vast ocean of space, with stars suspended at different depths like cosmic jellyfish in an infinite sea. For astronomers and space enthusiasts, parallax measurements provide something even more personal, a sense of connection to the cosmos. When you understand that the slight shift in a star's position is caused by our Earth's motion around the Sun, you realize that we're not just passive observers. Our very movement through space helps us understand it better. We're active participants in the cosmic dance, using our planet's orbit as a measuring tool. The method also connects us to a broader human story. When we use parallax today, we're participating in a scientific tradition that spans generations. From the ancient Greeks, who first theorized about stellar distances, to modern astronomers working with space-based telescopes, each generation has built upon the work of those who came before. This continuous chain of human curiosity and discovery reminds us that science is a deeply human endeavor. Perhaps most importantly, parallax gives us a tangible way to understand our cosmic address. It's one thing to say we live in the Milky Way galaxy, it's another to understand precisely where we are within it, measuring distances star by star, creating a three-dimensional map of our cosmic neighborhood. This knowledge transforms abstract astronomical concepts into something more personal and meaningful. The parallax method serves as our first cosmic ladder, the bottom rung in our climb to understand the universe. It's the foundation upon which we've built our understanding of cosmic distances, leading to discoveries about galaxies, the expansion of the universe, and our place within it all. Each time we use this method, we're not just measuring distances, we're reaching out across the cosmos, connecting our human experience to the vast tapestry of space and time that surrounds us. This is why parallax is more than just a measuring tool. It's a bridge between our everyday human experience and the grand cosmic scales of the universe. It transforms the night sky from a mysterious ceiling of lights into a vast, three-dimensional space that we can begin to comprehend, even if we can never fully grasp its immensity. Through parallax, we've taken our first steps into the cosmos, not with our feet, but with our minds and our mathematics. As we wrap up our journey through the fascinating world of stellar parallax, let's pause to appreciate the profound simplicity at the heart of this revolutionary method. It all began with something as basic as noticing how objects appear to shift when we change our viewpoint. This simple observation, something children discover while looking out of car windows, became the foundation for measuring the vast distances of our cosmos. The story of parallax measurement is a testament to human ingenuity and perseverance. We took an everyday observation and transformed it into a powerful tool for understanding our place in the universe. From Bessel's first measurement of 61 Cygni to today's sophisticated space-based observatories, each advancement has expanded our cosmic perspective, revealing a universe more vast and intricate than we ever imagined. What makes this method truly remarkable is its elegant simplicity. We don't need complex theories or exotic physics, just careful observation and basic geometry. It's a reminder that sometimes the most profound discoveries come not from complex instruments or elaborate theories, but from looking at familiar things in new ways. The universe reveals its secrets to those who learn to observe carefully and think differently. This leads us to an exciting question. What other cosmic mysteries might we unlock by simply changing our perspective? Just as parallax transformed our understanding of stellar distances, what other fundamental truths about our universe are hiding in plain sight, waiting for someone to look at them from the right angle? Perhaps the next great astronomical discovery will come not from a new telescope or sophisticated instrument, but from a novel way of interpreting what we already see. Consider how parallax measurements have evolved. What began as a method to measure nearby stars has become a cornerstone of modern astronomy, helping us map our galaxy and understand its structure. This evolution suggests that many of our current observations might contain deeper truths we haven't yet recognized. The key lies in our willingness to look at familiar phenomena with fresh eyes and open minds. The next time you gaze up at the night sky, remember that you're not just seeing points of light. You're witnessing a vast, three-dimensional cosmos that we've learned to measure and understand. Each star represents not just a distant sun, but a triumph of human ingenuity and observation. We've learned to use our planet's motion through space as a cosmic measuring tape, turning our yearly orbit into a tool for understanding the universe. This is the true power of science, taking simple observations and using them to unlock the profound mysteries of our cosmos. As we continue to explore and discover, who knows what other secrets await us? What fundamental truths might we uncover by simply changing how we look at the familiar world around us? If this journey through the science of stellar parallax has sparked your curiosity, we invite you to join our community of cosmic explorers. There's so much more to discover about our universe, and we're just getting started. Hit that notification bell to ensure you don't miss our next video. Remember, every great scientific breakthrough begins with a simple observation and a willingness to look at things differently. Who knows? The next person to make a revolutionary astronomical discovery might be you, simply by choosing to see the familiar in a new light. Until our next cosmic adventure, keep looking up, keep wondering, and keep exploring the magnificent universe we call home.